Tutorial 5, Part 2, Slip Systems and Schmid's Law. Slip direction, slip plane, and slip system. Dislocation, as you may guess, do not move with the same degree of ease on all crystallographic planes and all crystallographic directions. And if you still remember unit cells, different directions and different planes will have different atom distributions. Slip direction is the moving direction of the dislocation line, which is usually the densest packed direction. And you can find it by using the definition of the linear density. And energy required to move the dislocations in the closest packed direction, therefore, will be the least. And slip plane is the plane where the dislocation line moves on the plane, and just like slip direction, it is usually the densest packed plane containing the slip direction. And you can find the plane by calculating the planar density of that particular plane. And it is because the closed packed plane has the smallest atomic saturation, and the lowest shear stress is required for atomic displacement. And a pair of corresponding slip direction and slip plane will form a slip system, and the definition for slip system is defined accordingly. Slip system in body center cubic and face center cubic system. In face center cubic, FCC, the closest packed planes are 111, and for each unit cells, it contains 4 111 planes, which is within the 111 family of the plane, and which is non-parallel. And closest packed directions is the family of directions 110, and for each of those 4 non-parallel planes, it contains 3 such directions, and therefore the total number of possible slip systems in FCC is 12. And you can observe it in the picture of the left. And the plane 111 is look like a triangle, and you can remember it by remembering the shape of the triangle, which the 3 vertices are on the vertices of the cube itself. And the 110 is quite straightforward, just the edge of the triangle. And again, we don't consider the negative direction of this packed direction, as actually positive or negative, it doesn't matter, because when we reverse the direction of the applied stress, then basically the negative direction can be generated again. So we ignore the positive and negative direction of the slip direction. And that's why total number of possible slip systems is 12. In body center cubic, we can see here in the picture on the right, the closest packed planes are 110, and it is in a shape of a rectangle, and there is 6 non-parallel planes of 110, and the closest packed directions are 111 family of directions, and for each 110 plane, there is only 2 such directions. And how can you remember it? It is basically the diagonal direction. It is the diagonal, the first one, and the second diagonal direction, it is the slip direction. And total number of possible systems is again also 12. In general, metals with a larger number of slip systems are more ductile, and there is more possible ways it is because there are more possible ways, and which means that it is easier for dislocation slip mechanism to have happened. And that's why metals with BCC and FCC structures are more ductile than with HCP structures. You can observe it here on the list here, which I copied it from the textbook. And you can see that BCC and FCC crystal system have more slip system compared to the HCP materials. Dislocation motions under the normal stress for single crystal, which is very important. The first thing is dislocation motion can only be initiated by shear stress, and that's why somebody derived the law using the such principle, and it's called Schmid's law. And there is one limitation. This one can only be applied for a single crystal material. That is a material only containing one crystal, and the crystal itself is the whole material. And using the picture here, you can define that the resolved shear stress, this term is equal to Fs. Fs is the shear force along the slip direction over A1. A1 is the area of the slip plane, which is equal to applied normal stress times cosine this value and cosine this value. For the first cosine term, we represent the angle between the slip direction and the applied normal stress direction. And for the second cosine term here, we represent the angle between the normal direction to the slip plane and the direction of the applied normal stress. You can see here for this picture. Fs, the shear stress along this plane, is basically equal to F cosine this term, which is this angle here, and this is quite straightforward. And Fs is the shear force along the C direction. A1, as A1 is different from the actual normal cross section, and you need to multiply by a term which is related to this angle. And A1 is the area of the slip plane. A is the area of the normal cross section. And RSS, I just mentioned it. And basically, critical resolved shear stress is basically the minimum required shear stress for dislocation slip to occur. And the sigma y is the applied normal stress to produce the critical stress, and which is equal to F over A, which is the definition of the stress. And basically, that means when you apply this amount of stress, the material will start to deform at that particular direction. And we can use this equation to help us to calculate some or predict some dislocation or some deformation under expected force. Book problem. Consider a single crystal of nickel oriented such that a tensile stress is applied along a 001 direction, which is in terms of the crystallographic direction. Its slip occurs on a 111 plane and in a -101 direction, and is initiated at an applied tensile stress of 13.9 megapascal. Compute the critical result shear stress. Notice that nickel have a FCC structure, and which means that it is cubic unit cell. And because it is cubic, that is very, very important. It is cubic. The coordinates from the crystallographic direction can be directly converted to vectors in Cartesian coordinate. And be careful, this one is the mathematical format for Cartesian vectors. It is no longer a crystallographic direction. This one is a Cartesian vector which have a same direction with those crystallographic direction. And vectors normal to a slip plane is 1 on 1. We use this picture again. And 1 on 1 is here. And we use a definition of dot product. A vector A dot eta vector B is equal to the absolute value of A times the absolute value of B times their angle, the cosine value of their angle. And I need to emphasize it is cubic unit cell, and that's why we can use this one, which is only for cubic unit cell case. Other case is much more complicated and require knowledge from linear algebra. And if you forgot what is dot product, you can just have a revision on here, which is for Wolfan wiki. And you may ask, why don't we consider the negative vector? As I just mentioned, it will only apply the sign of the final answer, but not the magnitude. But as we are only interested in the magnitude only in these kinds of questions. And we basically just directly convert all the crystallographic direction into the vectors in Cartesian coordinate. And that's why 1 on 1, 0, 0, 1, and negative 1, 0, 1 is written here in this picture. Using the equation from the previous slide, which is the equation for dot product, we try to find the cosine angle between those two vectors to find the two cosine terms in the Schmid's law. In the left-hand side of the dot product equation, we just do the dot product, which is quite simple and straightforward. And yes, when you can do this, it is only for Cartesian coordinates. For right-hand side, you just take the actual value, and yes, I suppose you should know how to take the actual value of a vector, and you should learn it in multivariable calculus. And basically, we can find the angle, the cosine term, between the 1 on 1 vector and 0, 0, 1 vector, which is here, this term. And that's why we find the cosine, this cosine term is equal to this value, and this cosine term is stand for the angle here. And that's why we just plug in the value, as we have already given this value, and we have find this value and this value. And that's why we can directly form the critical resolved shear stress, and it is quite simple. And again, I need to re-emphasize it is for single crystal only, as obviously for polycrystalline materials, different crystals within the solid itself in different grains have a different orientation, therefore the correlation above will not be valid, basically. Example 2. How many systems will trigger if a single crystal of nickel oriented such that a critical tensile stress is applied along a 0, 0, 1 direction, given that nickel have a FCC structure? Okay, first we need to identify in this question, we need to first identify the possible steep systems, and basically how use the table, which is from the previous slide, or you can just basically remember it. And I will suppose I suggest you to remember it. Again, there is 4 possible steep plane in FCC structure. As you may remember, there are 4 triangular shaped planes, and their normal vector, again, we use Cartesian coordinate here as it is cubic and it can be directly converted. And because there is 4 plane and there is 4 normal vector, again, the sign of these vectors does not matter. We only consider shear stress magnitude. And however, as said, we still need to make sure these vectors have the same magnitude, because we will still use the dot product to compute the cosine term. And first thing is, how do we check it? We need to first check to see whether the dot product of the normal vector and the direction vector of force is equal to 0. If it is equal to 0, what does it mean? It means that there is no shear stress component on the shear plane, and that's basically no matter how large force you need to apply, there will not be steep system, and the steep system won't activate. And obviously, when by definition of the dot product, none of them is satisfied this requirement. Okay, so we then need to consider the respective steep direction vectors for all 4 steep planes, and which is corresponding to the steep plane's normal vectors, as I list out here in the table shown. And you may want to ask, how can I generate all these steep direction vectors? And there is one small trick. The dot product of the steep direction vector and the corresponding normal plane vector must be 0. And yes, this is because they are always perpendicular. Because the steep direction is always on the plane, and the vectors normal to the steep plane is always normal to the plane. And that means their angles between them is always 90 degrees, and their dot product is always equal to 0. And you can use this way to generate all the possible steep direction vectors. And again, remember that the negative values of these steep direction vectors are not considered because of the reason I have already specified. And yes, here is an example how you can generate these steep direction vectors. And because you remember that in FCC, for each steep plane, they has 3 possible steep direction vectors. And using the argument and the knowledge I have mentioned, you can generate this table. Then we need to check to see whether the dot product of steep direction vectors and the direction vectors of force is equal to 0. If it is true, then again, no matter how much force you apply on that directions, you will not activate the steep plane or the steep system according to Schmid's law, as there is no shear components on that steep plane and that steep direction. As the force direction vector is 0, 1, any steep direction vector having the form of xy 0 will have the dot product equal to 0, which is in the yellow part of the following table. And basically, that means we can reject these possible choices. And the rest of them, there is only 8 combinations left. And the first thing is to check to see whether the following system will produce the least value of the critical result shear stress, which is equal to the applied normal stress times two cosine terms, which is the two angles. Again, this one is the applied stress is constant. We need to only need to consider this value. Okay, so actually this value for all H system below have the same value, which is equal to 1 over square root 6. And that means H system will trigger in the above loading conditions specified. You can use two ways to do it. The first one is to calculate it one by one, which is lengthy, but this is not difficult because this is basically simple calculations. But you can also observe it, they are actually symmetric. And how can you calculate it? It is basically calculate cosine, the first cosine term first, and calculate the second cosine term. And using the methods I have mentioned in the example 1, which is again using the dot product equation. And yes, it is lengthy, but as you can see, it is just 1 times 0 or 0 times 1 or 1 times -1. It is very, very easy, but this is basically just lengthy. And if you are smart enough, you can just observe it, they are actually symmetric, and you can just calculate one, and you can already make this conclusion. Dislocation slip in actual cases, which is definitely polycrystalline materials. Dislocation slip is harder to occur in polycrystalline materials, as polycrystalline materials is composed of a number of randomly oriented grains. Dislocation line is hard to pass through grain boundary, which causes a great restriction to the dislocation slip mechanism. And this led to the rise of a stringing mechanism called the grain boundary stringing, which I will discuss it in the next part. As a result, polycrystalline materials is usually harder and brittle, while single crystal is solid, or material is softer and ductile.